The history of organic chemistry. What is organic chemistry? Organic chemistry is a branch of chemistry that is concerned with carbon and especially carbon compounds, which are found in living things. The beginning of organic chemistry. Most scientists consider Friedrich Wöhler's discovery of the synthesis of urea to be the beginning of modern organic chemistry because it proved that organic compounds could be made from inorganic starting materials. It disproved important theories and ideas concerning organic and inorganic compounds. And it sparked interest in further study of organic chemistry. In 1828, while trying to synthesize ammonium cyanate from ammonium chloride and silver cyanate, German scientist Friedrich Wöhler noticed that his product did not behave like ammonium cyanate should, but rather behaved and looked much like urea. After further testing, Wöhler was able to confirm that he had indeed made urea. This is what happened. Wöhler's experiment can be described using the organic starting materials ammonium chloride and potassium cyanate. These two react spontaneously, trading segments and forming ammonium cyanate and potassium chloride. This can be represented by the equation KOCN plus NH4Cl into NH4OCN plus KCl. This is also a double displacement reaction, meaning that there is an exchange of bonds resulting in products with similar bonds. Notice how, in this equation, it appears that K has simply exchanged places with NH4. We have our product of ammonium cyanate, but how is it converted into urea? The ammonium cyanate created in Wöhler's first reaction is then heated. Under this heat, the ammonium cyanate decomposes into ammonia and cyanic acid, which then react together to form urea, under the process of nucleophilic addition followed by tautomeric isomerization. Notice the two cycling arrows near the end of the equation. These arrows indicate a reversible chemical reaction. This means that in the reaction, the product yielded will react again to yield back the reactant. These reversible reactions will then reach an equilibrium, where the concentration of the products and reactants will cease to change, but they will still be going at the same rate as one another. Thus, the product and reactant will steadily and consistently go back and forth, yielding the product, then the reactant, then the product again, and so on. For an even more comprehensive look at Wöhler's synthesis, take a look at the GIF below. Wöhler's synthesis of urea is important for a number of reasons. One of the most significant of these reasons is that, in his synthesis, Wöhler disproved the widespread and popular theory of vitalism, which stated that all living inorganic things have vital force of life that differentiated them from inorganic things. In addition to this, Wöhler's discoveries sparked a new interest in organic chemistry. Intrigued, other scientists began to study and observe organic chemistry themselves, and manufacturers began to heavily utilize organic chemistry in their manufacturing, as it required much less cost and labor to create something in a lab than to harvest or acquire materials naturally. This leads into the invention of mauveine dye. One scientist who found great commercial value in organic chemistry is the English chemist Sir William Perkin. In 1856, while attempting to manufacture quinine, he accidentally manufactured the organic dye, Perkin's mauve, which was a rich purple color. This was the first synthetic organic chemical dye. Perkin patented this dye and soon began to make money off of his discovery. The mauveine dye, as it came to be called, became a hit. It was able to be stable while being washed, and it required far less effort to produce than other dyes, which were, prior, made from organic materials that needed to be harvested naturally. The mauveine also served as a substitute for the coveted purple dye, which, since ancient times, had been a sign of wealth and nobility, for it was considerably more difficult to produce. Chemical structure. In 1858, German organic chemist August Kekule and Scottish chemist Archibald Scott Cooper developed the concept of chemical structure when they noticed that carbon atoms can link directly to one another in order to form carbon chains. Previously, in 1857, Kekulé had proposed a theory that carbon is tetravalent, meaning that carbon has 4 valence electrons and is thus able to make 4 bonds to other atoms. Kekulé also helped in the development of the benzene structure. Although benzene's formula, C6H6, had been known for quite some time before this, it was difficult for scientists to determine its structure, because at the time it seemed impossible to have an arrangement of 6 carbons and 6 hydrogens that didn't violate the rules of chemical valence. Kekulé wrote a paper in 1865 suggesting a structure for benzene. This structure resembled a hexagonal ring with carbon at each angle and with a hydrogen attached to each carbon. Between each carbon would be an alternating double or single bond, resulting in 2 possible resonance structures. Years later, in 1890, Kekulé spoke about the creation of his proposed structure. He said that the idea came to him in a dream where he saw a snake biting its own tail, a common symbol of the Ouroboros. Kekulé's benzene structure is important because it helped to further establish the concepts of chemical structure. However, despite Kekulé's suggestion being considered the best of its time, it still had its flaws. Kekulé's structure showed alternating double and single bonds between carbons, but this is not true. All the carbon bonds in benzene became known to be all the same length, and since single bonds are known to be longer than double bonds, it was not possible for the benzene to have any alternating bonds. In addition, benzene's bonds were measured to be a length between that of a single and double bond. Thus, a new explanation arose. The electrons in benzene are delocalized, meaning that they are not bonded to any one atom and that they exist in orbitals that include multiple bonds and/or atoms. This is represented by a ring on the inside of the carbon bond hexagon shown in the modern benzene structure. Organic chemistry and medicine. In the late 19th century, the pharmaceutical industry took off with the manufacturing of acetylsalicylic acid, or aspirin, by the company Bayer, located in Germany. Pure aspirin was first synthesized in 1897 by chemist Felix Hoffmann, a worker under Bayer, via an esterification reaction. Prior to then, salicylic acid from the bark of white willow and poplar trees had been used, but it was irritating and bitter to ingest. Organic chemistry and petrochemistry. The discovery of petroleum also helped to develop organic chemistry. Chemical compounds and hydrocarbons called petrochemicals can be extracted from petroleum. They include olefins, like propylene and ethylene, a building block of organic chemistry, and aromatics, like benzene, toluene, and xylene isomers. Many products can be derived from petrochemicals to manufacture a numerous amount of commonplace items that people use every day, from plastics to medicine to TV to DVDs to computers. Basically, everything not made from plants, rocks, or other living things are made from petrochemicals. The petrochemical industry grew rapidly throughout the mid-1900s, and it now plays a major part in both society and in the economy. Organic chemistry and biochemistry. In the late 1800s, scientists were really beginning to understand and develop biochemistry, which is the study of chemical processes within and relating to living organisms. Although the two are different, biochemistry and organic chemistry overlap. Biochemistry includes studying the reactions of organic chemicals, and it also uses many of the concepts and ideas surrounding organic chemistry. The development of biochemistry brought on new uses for organic chemistry. Organic chemistry today. Since the beginning of organic chemistry, around 9 million organic compounds have been discovered. That's 90% of all discovered compounds. Scientists today continue to make more and more observations and discoveries surrounding organic chemistry. Works cited.